Is recording. Perfect.
All right. This is the last lesson we have in the section. This is 113. It's really going to combine some of the ideas from the first two lessons together and kind of give one little next step that's going to help us see really quickly what's the probability of different values. Okay, so the main thing, and some of this is a review because we've hit on this quite a bit. For one thing, I need to tell you that the outlier we've already established is 3.4 sigma from the mean. Okay, the book and just the high school level kind of, downsizing of that, they say any outlier is over 3 sigma. But because I want you to get used to it, I want you to know 3.4 sigma. You know, you get to college stats, you already know that. So we're going to keep going with 3.4 sigma. Okay, but if you see something in the book, remember, doesn't matter, disregard, we're going with 3.4, and that's how we're going to move forward. So I want you just to have the same knowledge and not get to college and say, wait a minute, wasn't it 3? And they'll say, no, that was stats on training wheels. That's not right. We're going to go for the full thing, right? Okay. So think of it this way. If you have a small sample, then the outlier makes it not a normal distribution. So I want you to imagine this. If I have this, I'll just write it down here. If I have some problem sets, or I have a set of numbers, and I have 1, I have 2, I have 2, and I have 84. Right? Because it's only 4, there's only 4 values in that set. So you can see that there's no way you're going to end up with a normal curve. If I ended up, and this was, instead of 84, it was 3, then I'd say, well, it's a normal distribution, but there's so few elements as well, it's not going to be reflective of a larger population. It's just kind of a very basic explanation of it. But if, say, you have a big sample, a huge sample, then you can eliminate outliers. Think of it this way: you have 1,000 people took 1,000 people take an IQ test, right? There's going to be a lot of columns for every single score you can get. There's going to be more than if I had 10 people doing it. So if you have 1,000 people taking IQ, and Albert Einstein was one of them, this would be an outlier. It'd be way over here, really high IQ. Right? But if I just want to draw information and make some kind of inference, which we'll talk about tomorrow, about what my sample size says about a population, what I can do is I could take Albert Einstein's 160 IQ and just eliminate that outlier. I can say we'll take away the ones that are just so far out because I have 1,000 different test scores in between. You see how if there's like a huge sample size, those outliers don't make much of a difference. If there's only 4, like this was here, then it does make a huge difference. Okay, so you got to be careful with that. Some of this is going to be judgment call with outliers. Just look to see what you're paying attention to, and we'll visit that again when we do example 1 over here. A histogram. The thing I wanted to bring up about this is this isn't related to this topic. I'm just going to use this graph to show a basic histogram you all know. So a histogram, remember, is talking about values related to the mean. And would you say this is basic or normal distribution? Normally distributed? Okay. So if this was normally distributed, then I would be able to, right above it, make my normal curve. And that's basic, right? What we need to know, and really prepping you for calculus next year, is that the area under each bar is proportional to the frequency. So that means the area of the bar, this bar has more area. So this value, whatever it is representing, the value, it has more frequency. It happens more often than this bar over here. It's very intuitive. It's very like a direct correlation. If the bar has a greater area, that means there is more frequency of that value. Okay. So if we wanted to find the area of, let's say, one that would give us some problems. If I wanted to find the area of the values that had a score of 8. This one right here, it would be this area, which is for a rectangle. What is it for a rectangle? Length times width? Right? Too easy of a question. All right. So for a rectangle, it's length times width, right? But remember, we would be using the normal curve, the normal distribution, also to make estimations for probability of things happening. So if we wanted to really find with the histogram the area of each bar is proportional to the frequency, eventually what we'd have to do is, instead of bars being this wide, right, because look what I have above it. There's all that space above there that I did not get the area of that. So the bar graph definitely gives us more of an idea of the probability. But what can I do with this bar to make it more accurate? If the outside top edge is always going to hit that curve, what could I do with that bar to make it more accurate?
Make it thinner.
That's it. Not just make it thinner, but break this interval of 8, break it up maybe into 7 to 7.2, 7.2 and greater to 7.4, and so on, so that you'd have smaller bars. You could see that in that little area, if I broke it into smaller bars, I would be able to find the area of that. And what I could say is the summation, so all of the areas added together of those 3 rectangles, will give us the actual area for 8. Okay. What's coming up in calculus? Calculus allows you to look at an interval and say if this is the interval of 1. We'll just call this 1. It's not an interval, it's 1. What we'll be able to do is take the upper limit, lower limit, and if you take what's called the derivative, between these 2 values, you get every single bit of area under there. It's the next step. There's a bunch of baby steps to get to that point, but when you get to calculus, you're taking the derivative. It doesn't matter. If you had a really, kind of a sine curve, not really, transformed up, between these 2, this would be very, very hard to find the area of this if you didn't know calculus. But you take the derivative between these 2, or along this interval, and you'll be able to find all the area, every single bit, all the way up, if you know the function and the interval you want to look at. Okay, so that's where we're going, but I just needed to say that so that you remember back to that, and you'll know where you're going when you get to the calculus part. Next is an aspect of being skewed. So we're gonna have some graphs that's gonna say, is this a normal distribution? And you might say, well, it appears to be a normal distribution, but it's skewed to the left negative, or it's skewed to the right positive. Okay. So the one way I'm gonna help you, bless you, to remember this is, you guys know I have a dog, right? Have I talked about that this year? Yeah. A little bit.
No,
Just one thing, just one folding feature film. All right, my dog, because of the breed, when she was born, she had her dog tail docked, so she doesn't have a tail. So for me to show you this, it's really the tail to the left or right. I think he's my cat. You didn't know I had a cat. I do. His name's JT. So JT has a long tail, and then he's sitting over here. Kind of a vampire cat. That's cool. You wouldn't mind seeing that. Oh, that's not bad. It's cat. The tail is facing which way? Left. Towards what? Positive or negative numbers? Negative numbers. So when we have a skewed left negatively, what we end up with is this tail that's long on the left side. You see how there's some aspects here? Let me make it a little bit better. It's just a little bit better. Okay. You see how there's more values. There's just a few more values that are lower, right? So this would be, there's not many, but there's a few people that scored really low, but the cluster, the main scores were a little bit over to the right. So the tail goes left. If the tail goes left, it's skewed left negatively. Okay. It's skewed left negatively because there's some other scores that disrupt this being kind of a perfect normal curve. Okay. What do you think about skewed right positive? Skewed right positive is going to have my cat's arch enemy next door. TJ. That's right. Yeah, they're stray, so they have one ear that's a bit funky. Okay, there's a long tail, and then we go down. So if it's skewed right positively, that just means the tail goes over the right. Okay. That's a real basic way to remember it, but these things, you kind of need something basic because it's so foundation material. The other little bit here is when it's skewed left, the mean is less than the median. To find the median, we look at the numbers. If I'm looking at this problem set right here, to find the median, I just go out from the middle. They're all sequential. My median is 3, right? This is a different kind of skew, and we'll talk about that when we get there. Or it's one of these, but we'll get there. The mean is less than it because, say if, I'll give you a good example. If you worked as a waiter or a waitress, okay, if you were doing tables, okay. The first week, 5 days you work, you got $10, $12, $13, $12, $10. That's just what you got. Average of maybe 11. Okay. The next week, right? The next week you had really bad tips. You averaged, you had a 2, a 3, a 4, a 3, and a 2. Okay. Now that second week of bad, low-paying tips. What does that do to your overall average? The overall average the first week was 11. The mean for the second week, if we include it, first and second week, is going to be higher or lower? Lower. Because you got a bunch of low, like these were tips. There were a bunch of people that gave you low tips, so there's more over here. The tail is going to the left, skewed left, negative, right? And that is going to make your mean lower. When you get a bunch of just random lower, tip days, then your average, your mean for the tips for those weeks is going to be lower. Same over here. If your average for the first week was $20, you got a big spender the next week, you get 100, you get 80, you get 60, you get 50, right? $100 tip. Then it's going to be skewed right because there's not going to be many options over here. The $100 might be one person, but it's skewed right positively. So in this case, the mean is going to be greater than the median. Median isn't going to change so much, especially if you have a lot of figures, a lot of values. But you see how that would kind of work? Think of getting a tip. I feel like that's one way to approach it. Okay, I'll start this. These are basic foundation ideas in order to interpret data. Here is the functional aspect we're going to deal with today. And this is called the normal probability plot. All it does, the key to this, is it's a plot of the z-scores. It's a plot of the z-scores for each individual value. So all these are values. All these are values. Say if this was just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This dotted line in the middle that I made is 0 standard deviation from the mean. So where these points cross this dotted line, that's where the mean value is located. Now, the values that are down here, they're -1 standard deviation from the mean. The values that are up here, up 1, are +1 away from the mean. So it's basically just giving a plot of all of our points. And you could easily tell, are there any outliers? Are there any outliers from this graph? Where would I find an outlier? You see any outliers? This one way down here, right? That could be -3.4. Kind of ran out of room. But you can see most of them are grouped along this best fit line. So we plot all of them. We have to find the z-scores for all the values. We plot them. And then the best fit line is going pretty much right through it. You guys remember best fit line? We have data. So why do you think, and talk with your neighbor, why are there more dots? Right around this area in the middle. Why are there more data points right around this point in the middle? So talk to your neighbor, 10 seconds. This one's real quick, real quick, real quick. All right, 3, 2, 1. Yes. All right. Who can tell me with confidence, why are there more points, more values plotted right there in the middle? I heard a lot of good things, so everybody knows. It's just who's bold. Yes. It's the mean, and when we have a normal distribution, where do we find most of the points? In the middle. How many percent is between 1 standard deviation from the mean? 68%. Most of them are 1 standard deviation from the mean. So if I look here, most of my points should be between 1 and -1. That's one way to know, hey, this is a standard deviation. This is a normal distribution. Normal distribution. So we're just going to plot the z-scores. If you know the mean, right? If you know the mean, you know the standard deviation, and you have a point, you want to see what the z-score is for that point. Plug it in here, you find the z-score. We're going to have to do that a few times, but these problems are involved, so you don't have as many to do. This one problem has a few things you have to do. And then it gets really quick once you start inputting. All right. So from the graph, we can see if it's normally distributed. The points will follow the best fit line. They'll be close to the best fit line. And most points are close to the mean, which makes sense. If I look at a normally distributed set of data, most of the points are towards around the mean. Right? And what that's also saying is most of the points are within 1 standard deviation, and they are going from least to greatest, which is always going to happen. This best fit line is always going to go up and to the right with a positive slope. Now, it also lets you see outliers really quick. I can see my outliers because, or even if it's not 3.4 or above, sometimes we'll drop some outliers because it's going to disrupt the probability from the chart we can get. So that's kind of a judgment call. And then if it's skewed left and it's negative, we have the tail going off to the left. So we have the tail to the left. We know that's right. Where are most of my points, though? Most of the points? To the right. Most of the points, we can see the curve goes up. This is frequency here. So when we have a skewed left negative, we end up having most of the points over to the right. Which is okay, but you know, if I gave you this right here, say if I gave you another one, you know, we have this. What is that? Skewed what? Think about it now. Very good. Good, no? No, you had it before. It's skewed to the right because we have most of our values are in the lower range of our values. Most of the plotted points here. So we can see that when we have a tail going off to the left, or excuse me, to the right, it's skewed right. The tail always faces the direction it's skewed. But most of the points are to the left. Most of the points are to the left, so this one would be a skewed right. But I would say it's normal distribution. Why would I say that? They're pretty much on the line. It's just going to be skewed quite a bit. And the next couple lessons, we're gonna get into analyzing that aspect. It goes a little deeper than this, a lot, but we're going to take one step at a time. No problem. All right, that is the basics for what we have to do today. I want to go over these examples, but we'll start with this one right here. I'm going to move the computer in a sec. But looking at example 2, is this a normal distribution? What would you say? Talk to your neighbor. I'll give you 15 seconds for that.
That was not a judgment.
It's the fit.
That works.
Hold up. One other thing. Sorry, everyone at home. Yeah. Okay. All right. Who has some input on this? This is interpreting a graph too, so you might have different input. We'll see if people agree with you. Anybody want to speak up? Well, what are some things we notice about this? Think it.
A lot of the points aren't around the line of best fit.
The line of best fit doesn't have too many points near it. Too many points. And we could see that if here's 0 standard deviation, most of them are, actually if I kind of did it, let's say this is -1, and this is 1. Okay? Are most of the points within one standard deviation from the mean? No. So if I end up with a bunch of data that doesn't have 68% from the mean out one standard deviation, that's suspect. I'm suspect. So yeah, if it's not a good fit, these points are kind of spread out all over the place. I probably should have made it down through this a little bit more. But you guys get the point that if it's not close to the best fit line, we're going to not call it normal distribution. All right, how about this last one over here? Yeah, we can kind of see that pretty well. What about this? I know it's hard to see in the back, but I'll describe it. The points are along the best fit line, but there's more of a cluster down here and over here with a few in the middle. All right, 30 seconds, talk amongst yourself. Love the delay. All right, let's bring it back. All right, what does anyone have observations or think about what this would look like? What do you think? What would this look like as a histogram? What do you think? Or maybe some observations. I went to like level 10 all of a sudden. What do you guys think? Normal distributed or not? Yeah.
Well, like on a histogram, it would look like there's one patch over here, and there's like a blankish space, and then another patch over there.
Great. So if I was making this my histogram, there might be some bars over here. There's a couple in the middle. Some over here on the right. Is that normal? No. What do we need? We need most of the points to be, most of the data points close to the mean. That makes sense. It's a bell curve. In the middle is where they're all going to land. And I see it. I see the nods like, yes, 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 we know. It's a good nod. I see those nods. It's good. Right. I want to show you one thing here. Let's go to the Word doc. Pull it up. No, that's not it. There we go. All right, we have some of our statistics here from the survey we took. This is tall. I'm going to go up a little bit. Number of seconds you can hold your breath. Quite a few down here, 10 seconds. Looks like here would be our mean, pretty much. What kind of distribution is it? Is it normal? And there's any skewed aspect? Are there any outliers?
Yes.
Okay. Is there a tail? Is there a tail in one direction or the other?
Yes.
So it's skewed to the, towards what numbers? Positive. It's skewed right, positive. Okay. So I know that my mean is likely here because there were a frequency of 30 right there. There's 30 values that are for that column, for that interval. But since it has a tail to the right, where is my mean going to be in relation to my median? It's the very center number, and then the average of those, of all my data. Most points are going to be to the left, but I think that's what we just talked about. But over here we had the median and the mode, right? So when we have a tail over to the right, yeah, as included, the mean is going to be moved over to the right because we added those scores over here. This is like when you got the tips the second week of the 100, the 80, the 60. Your average, your mean for the 2 weeks, it moves over to the right. You see how that would work? So normally distributed, skewed right, positive. We'll go with that. How about this one? Is it normal? About? It's about normal, right? It's about normal. What would we call this over here? Likely an outlier, right? If I wanted to make a conclusion from this bell curve that's created, I probably would eliminate that option. But we can also look and see, okay, 85. 85, if I could find the standard deviation and the mean of this, I'd be able to figure out what the z-score is and if it's an outlier. Okay. We can do this. All right, next. Hours that you get sleep.
Or
Yeah, they're out. We don't even want to look at that. We don't want to be reminded people sleep.
I don't think it's possible.
I don't know either. Oh, don't worry. It's possible. It's possible.
I'm one of those.
Is this normally distributed? Yes or no? Are the majority of the values at the approximate mean of this data? Approximate, right? But there's this incontinuity here. So next week when we get into kind of testing how close it is between the sample and the population, that's where this would come into play. This is kind of a confusing one for this week, but we can make a lot of inference just from this. You know, I know my mean is probably around here, right? But I don't have. This is a pretty big frequency. Look at this. This is 32 or so. This is 25, and then down here we have 8. So there's a big inconsistency here, right in the middle, where it should be what? It should be way up here. So I would say this is not normally distributed, but there are some normal elements we are seeing, and we have outliers there too. Okay, let's knock this one out and look at the clock, and yeah, we're running out. Shoot, sorry guys. When I film, sometimes I take too long. All right, it looks like for this one, all right,